today that I'm really happy to be here, to see some familiar faces, but also for those who I'm seeing for the very first time. And so I think we're going to start now. This is the abstract. I've chosen to talk about this thing called the automatic formalization of math reasoning, which we'll talk about. And it starts quite interestingly. So this is a tweet from my Twitter account when it was still called Twitter. And there I was really upset with this theorem. It was in the December 18th, 2022. For those of you who do not know, I was also a student at this university, and this was ahead of my analysis 1 exam. And as you can see, I was pretty upset with this setup. If the proof is clear, then why do you mention it? And if it's not clear, then why don't you talk about it? And then there's the name of the book, which is the undergraduate real analysis. This was the name of the book. I saw this meme as well, and I thought it was really funny. I think it really expresses how I felt at the time. But this talk is not about memes, even though I have one more meme here. But maybe we'll move on from here. What I really want to talk about is the fact that we have so many proofs like this one, especially as mathematicians, and the arguments are obscure, the arguments are not obvious, and there are lots of gaps. And keep in mind, this was the pre-AI historic era, so there were no LLMs to help you with anything. And really the takeaway, my 2 cents here are that the logic is in a sense compressed. The arguments, we don't see them in their full length. And the reasoning is partially omitted for the sake of comprehension. And that means that in order to not write 10 pages of proofs for a complete proof, I just simply write a 2-liner and reference some text or some other theorem, and this we'll talk about. But also the unverifiability, because in my case, and keep in mind once again, this was the pre-AI era, I didn't really have any way to verify that this proof is correct or not. And this is a simple example, of course. And for that, I would like to take a step backwards. There's this thing I want to talk to you about, which is the mathematician's dream. And it started in the 1920s with Hilbert's program. And this guy, Hilbert, he's a mathematician, and he asked a really interesting question, which is, can we verify all of mathematics mechanically? And what this means is, can we combine all of mathematics into one specific framework? And there are some efforts that outline an idea that is similar to the one that we're going to discuss today, such as the Bourbaki group. They're a group of mathematicians who wrote a very large non-digital database on proofs and theorems under the collective name of Bourbaki, for those of you who know. And then came the so-called QED manifesto, which was in the hopes of achieving this mathematician's dream of having this digital repository of, well, not all of mathematics, but a lot of mathematics. And of course comes the question, today we are in 2026, what happened and where are these people right now? And so for that, we need to take another step backwards. And just to be clear, if you haven't figured it out already, formalization is simply taking an informal argument, like the one we saw, and writing it into a formal proof that can be verified. Here I summoned back the corollary, which I tried to make fun of on my Twitter account. And this is very simple problem. Informally, let's take a look at the proof. This is the one where you guys are supposed to laugh and explode and laughing. But anyway, I'm just kidding, and I'm actually going to give the proof, not like in the meme. And effectively, you don't need to be a mathematician to understand what's going on here. All I want is two ingredients. The first thing is the delta epsilon definition of a limit, and the second one is this lemma, this property. And then applying 2 to 1 gives the result. Now, this is a more expanded proof, I would say. And I think this graph will show you guys exactly what I'm talking about. So we have a theorem or a result that we want to reach, and we start with a definition. From this definition, we get the lemma and the theorem, and we combine these two to get a final result. Now, this is a structure of dependency, as you can see here. You start from the definition, and the theorem depends logically on the definition, which means it is derived from it. And then you do this combination, just like we saw at the back. We combine these two things, and we get the result. So, a little bit more about this graph. This graph is one where statements are the nodes. So the big circles in the middle are the statements that we want to deal with. The arrows are the logical dependency. I think there's a typo over there. But also, most importantly, it is acyclic. And what acyclic means is that it doesn't complete the cycle. It doesn't make a full cycle. And the reason for that is that a statement cannot reference itself. A statement cannot depend on itself. It's a very famous, I think it's a very famous result, a very famous paradox by Bertrand Russell, where he looks at the set of all sets that do not contain themselves, for those of you who know. But that led to some stuff, and from there we say, okay, so this graph is going to be acyclic. And this gives us the DAG that actually I think Insights is working with, and I think you'll be working with throughout this datathon. So let's take a look at the compression problem. Let's take a look at what the actual problem is. Because I come here to you, give you this talk, and I tell you there's a problem and you want to talk about it. And so the problem is that if you want to write a good proof, and by a good proof I mean a proof that you can actually read, you need to be you need to compromise in some things. You need to put some key ideas, and you need to perhaps sometimes reference some statements that you cannot afford the time to prove from scratch. And this is the nature of mathematics. It will be completely obscure if you have to, for example, mention all of the results in probability theory to prove, for example, the recent result. It is a logical progression of how the authors are writing, producing mathematics so far. And the formal proofs, as you can see, is they're much, much larger. They're complete, but as I said, you have to write 10 extra pages by notes, by the way, just to make sure you guys are focused. These are the statements that we need in the proof. They're complete but verbose, and the insight really here is that this proof is, in a sense, it's a compression of the original DAG. And what this means is there is a big proof which has a lot of nodes, just like this one. And there is a verbal proof which is written in natural language, which does not have all the details or all the proofs to the statements that are given. And this is effectively what's happening. And the question really here is, can we recover the original form of proof from the compressed one? Can we take a proof that's written in natural language and figure out all the missing pieces, all the missing steps, and fill them out. And this is, oops. And we'll return to this question later on. And here we have this QED manifesto. I want to just give you more context, because now that we've defined what a formal proof and what an informal proof is, now we can talk about it. So what the QED manifesto guys did at the time in the 1990s, each person would create a different proof assistant, a different formal language that is used to describe in mathematics. To name a few, there's Isabelle, COQ, there's Lean, the one that's most popular. But the idea really here is that there's always this hope that the community will just look at all of the proofs that we have, all of the papers that we have, and they're going to take care of it. They're going to formalize everything. But if you think about it, what that really is doing is it's doubling the effort. If I'm an author and I'm writing a paper, I don't just have to write it in natural language, which is the standard these days. I also have to formalize it. And that's double the effort. And that's why this hope is too weak. We cannot really rely that someone will take care of it. I think that's what led to the slowing down of the movement at the time. There is a more recent shift by Kevin Buzzard and Peter Scholze in the Lean community. Lean is a formal language to write formal proofs. And they're working, for example, Kevin Buzzard is working at Oxford on the Fermat's last theorem, which, for those of you who know, is an 80-page theorem that requires lots and lots of fields of mathematics intertwined together. And just to give you a perspective, he's been working on it for 2 years now, and he still has a grant that goes for 5 years, and they're just working on this one single problem. That's actually how difficult it is, because not only are they working on a very long and very difficult proof, they're also decompressing it, which means the volume of mathematics that is being handled is much, much larger. And the repositories, the formalized amount of theorems is not enough to keep up. So what Buzzard and also Scholze is doing the liquid tensor experiment generally is they're using this as an excuse to build the libraries. So I start from Fermat's last theorem, and I say, okay, I'm going to look at the theorems which I'm missing. Let's say if we go back to this same graph we took a look at, I start at the top, well actually at the bottom from Fermat's last theorem, and I look at the dependencies one by one, and I try to go. And you can imagine this going all the way up to the point where we have the proofs for the formalized theorems. And this is really the mental image I want to leave you with. So that is what's happening right now. But unfortunately, this is not enough. As I said already, this is taking 5 years just for one big theorem, arguably, but it is still taking a lot of time. And so the solution really here is to introduce automation as a solution. By automation, we mean instead of depending on crowdsourcing and depending on 15 individuals to build a formalization for a specific section of mathematics, what we could do is we could get 50 agents. And these agents would, these are AI agents, of course, and these would, the work would be delegated. So that is really the idea of auto formalization, to put the two words together. And maybe let us rephrase the mathematician's dream once again. It is taking an input of a proof or a theorem, and then you take this theorem, you figure out the DAG structure for it, which is the nice graph that we saw in the beginning. You try to decompress it, figure out all of the gaps, and you get the output is a formal and verifiable proof. I want to go back to the very first corollary that we proved, which didn't really bother me. And I want to ask you guys a question. That was so. My question is, if that's the statement that you have in front of you, how would you reconstruct the DAG for it if you have absolutely no information? You're just giving this corollary as correct. You're giving this corollary as truth. Of course, it is correct because it is verifiable. But I want you to take this example and generalize it to more difficult theorems. I want to prove a very difficult theorem formally, and I have some helping statements, but these helping statements in their own right are not proven. You have absolutely nothing. So what you need to do is, you need to figure out the theorem that you need to use, the definition you need to use, and the lemma. And the graph expands to thousands of nodes and thousands of edges. It's that big. I think I remember, and I think we'll talk about this in a moment. It's the work by Gauss Inc. They were working on formalizing a specific proof, and they spent I think it was thousands of terabytes of RAM just to run a model that could process everything. And that maybe gives you a flavor of the problem that we're dealing with right now. Now, obviously, this is the dream once again, and the graphical reconstruction, I think, is pretty clear right now already. And the question is it possible? And let's see. So there is a certain gap, and that is the following. Of course, as I said, one needs to infer the nodes and the edges and the subgraphs. In the example that we just saw in the very beginning, we had basically no subgraph. We had nothing to start with, not even a single statement, just the result. And this is the type of task that is required to be solved. And of course, you ask the question, what could possibly go wrong? I'm standing here right in front of you, and I'm telling you, you just need to do 1, 2, 3, and 4. But how are we going to do it? And what could possibly go wrong? Well, let me tell you. A single proof can have two ways of describing it. It can have two different ways of writing it down. I think some of the very famous theorems, they have so many proofs. I think the fundamental theorem of algebra has like 15 proofs or something similar to that in every single field of mathematics. And they all lead to the same result. But the DAG, the directed acyclic graph, the full formalized version of the proof, is not unique. That is really the catch here. If you can prove a theorem in many different ways, then the operation where you decompress the natural language proof into a directed acyclic graph is definitely not unique. And from there, we do this thing where it's called the Ill-Posedness problem. And what that means basically is, if you have a DAG graph, you can write down the proof for it. You can write down the proof in natural language because you know all the pieces and you can bring them together. But if you try to do it the other way around, there is more than one way to do it. And that leaves you in a space where the DAG could be one of so many solutions. And that's usually not a nice class of problems to deal with. But then there's also this gap, which is, of course, the semantic gap. I can say something right now, and it would mean a completely different thing to maybe 2 people. And this is really what we're talking about here. So if we have this example, which is, I would say, semantically ambiguous, then the standard argument could refer to so many things. And these are just some examples. So it could refer to a direct calculation. It could refer to a 3-page lemma from another paper, or a highly not trivial argument, which is simply not easy to understand. So I would say not so clear. And the current landscape is the following. I wanted to give a glimpse into what people are actually working on right now. And that is the following. So the first paper which I read, which I thought was really nice, is the paper called Informal, which builds the skeleton of the proof from the natural language. So it doesn't go all the way. It doesn't go all the way, but it goes somewhere. And this is basically roughly what it does. It identifies what pieces do we need to formalize. It doesn't formalize them. It just tells you this proof needs these pieces. And there's another very interesting paper, which is, by the way, the main author on is an undergraduate student. Very interesting remark here, and perhaps a motivation for all of you. This lean agent is an agent that expands and verifies the proof form. So it takes the natural language and it tries to expand it and verify it. It takes a proof, which is a natural language, and it tries to fill in the missing things. And it has had lots of success. But I don't want to cram you with too many statistics. Let's put it this way. Obviously, these are all approximations to the reconstruction problem. And I just want to take a moment and think about what working towards this dream, this mathematician's dream, would lead us to. And we already have some partial progress towards the solution of this problem. We could think about hybrid human-AI collaboration. We could think about papers that are much well-structured. We could think about papers that are formally verifiable, papers that you don't really need to summon 3 or 4 experts in the domain to peer review the paper, because you know it is correct, because you can formally verify it. And obviously, it is a very good learning tool, because if you try to do this process, even as an undergraduate, if you try to take a proof and you try to find the missing pieces in that, you don't really need some software, you don't really need lots of setup on that. You can just think about your next math problem, try to sit down and write down all the ingredients you need to solve this problem, and let's see how you can put the pieces together. So if you do this with the added layer of the formal verification, that is a source of truth which is verifiable, that tells you if you're doing well or not, then you have a very prospering future in terms of the learning process, in terms of how much information you can absorb and handle at the same time. And obviously, this is the thing that many people do not like to hear, and it's probably cliche for the amount of times that's been said so far, which is that AI will replace mathematicians. I don't think this is going to happen. I think it's only going to happen to the subset which can be outranked and outworked by good organization, good collaboration with the agents, with the technology, and trying to stay up to date with the latest events. And I would like to conclude this with a proposal. So in the same flavor of the undergraduate seminar, which you've all heard about and probably attended, here I am proposing a learning project for you, which, if you're interested, you're of course more than welcome to talk to me after the talk about it. And that is basically, we take this DAG problem and we treat it as a missing value prediction task. And the missing values are always going to be the statements, but also the dependencies of these statements on each other. And we can work our way with this setup. There are, of course, some strategies which one could think about, and I think it's a very interesting learning project. As I said, there's lots and lots to learn from. So if you're interested, definitely let's talk. These are the resources I used and cited throughout this preparation of this presentation. The Lean Asian paper is a really good paper, so is the M2F. And if you want to get a taste of history, a taste of the 1920s and the dream that Hilbert was preaching, you can, of course, refer back to the original papers. And I think Alex is going to give a talk on, I think next week, on Gödel's incompleteness theorem, where Gödel actually shattered all of the hopes of Hilbert in a certain way. I'm not going to say too much about it, but it's a very interesting talk and you should definitely attend. In the end, I would like to thank Ahmed Madri for the very warm invitation and, of course, for the very nice words. And I just want to say that he's been doing an amazing job. Of course, when I started with the Math Society, of course, I was doing lots of things. I tried to do as much as I can, but I never had it in me to achieve what Ahmed has done. And this is a society that 2 years ago barely got extinct, and now it's alive more than ever. I don't think I've ever seen anything like that before. So I would really like to thank Ahmed for the work that he's doing. So enough with the glazing, and in the end, I would like to thank Pablo Santos Guerrero for the fruitful conversations we've had about this topic. And I think that's it.